In this presentation, we want to talk about the controlling buck DC-DC converter, and we want to talk about the simulation, from simulation to modeling, and we were trying to cover all of these below. First of them, I want to introduce the buck DC-DC converter. And what is buck converter? A type of DC-DC converter that step down the input voltage to a lower voltage for the output. And we used DC-DC converter in many cases, for example, in chargers for the laptops or mobiles, or in the, for example, biomedical area, and used, I can certainly say that it tremendously used in all over the world. And the final step of this page is about how it works. The converter use the inductor and capacitor to regulate the output voltage to a specific level of the voltage, for example, and specifically to a lower voltage. For example, we reduce the voltage from, for example, 110 to 5 volts or 10 volts or 12 volts for chargers or something like that. And now I want to talk about working principle. And when we talk about working principle for DC converter, there are three subjects that become very important for this. First of them is mode of operation. The mode of operation means that there is two operates for DC converters. One of them is continuous, or one of them is discontinuous, and it depends on for the current mode. And there is discontinuous for current mode and discontinuous for current mode as well. Second of them is the components, the main components for DC converter. First of them is it includes from inductor, diode, capacitor, switch, and these are the main things to build to make a converter. And third subject is about the efficiency. One design must balance power efficiency with voltage regulation stability and output ripple as well. Now let's talk about the strategies of control. First of them, I want to talk about the most common and most important, we can say, the most important method of strategy or method of control that called PWM control. Nowadays we use PWM controller in every single controllers because it's really easy to install and to use, and its regulation involves the varying the width of the switch pulse to adjust the output voltage. And another strategy is a feedback controller that we can merge with any kind of controllers. If we use the feedback, the external feedbacks for any controllers, we can use feedback controller as well. And It adjusts the duty cycle of, for example, the PWM or any kind of controller signal to keep the current or voltage constant. So, and the third of them is current mode controller. It's an alternative to voltage regulation, and that be used inductive current rather than a PWM signal width. And now let's talk about the design criteria. First of them is about the components, component selection, the most important things. You have to measure the, for example, inductor, the capacitor, the switch, and any kind of things, the diode. Which diode you have to choose, and which capacitor you have to choose, or inductor as well. And the second of them, you have to have a PCB, a right PCB. The most important things for the electrical things. You have to design a perfect PCB for example, controller or anything else. To have, for example, the best optimization or verification or validation as well. And to ensure a stable power delivery to output as well. And the third of them, the transient response testing. What's this? It's the measuring, for example, the converter can handle the quick change or the very quick and immediate change in load or in the input voltage or not. If all of these are perfect, you can say our design is really nice and good. And let's talk about the simulation and modeling. We have a design and we have a PCB or components. First of all, we have to make sure about the components or the design. And because of this, we have to use simulation because the PCB or components have lots of costs. And you have to pay to buy, for example, the PCB or the components as well. But you have to simulate and model in the computer or PCB very well and very easy. First of them, you have to use the suitable software like MATLAB, LTSpice, or PC to simulate for example, PCB or any controller. And then you have to design an optimization. Use for example, which of them is better to use for example, improve the efficiency or stability or anything else. And the final step about the simulation and modeling is data verification. You can you can get the results, and you can, for example, get the problems, errors from that, and you can improve all of these in the virtual way as well. And this is very, very important to design perfect things. In every single things, I think it's better to first of all simulate and model, specifically in electrical things.
Hello, this is Ali Yusuf Adami, and I'm gonna keep going with the PowerPoint. As my friend has told, the buck converter is a voltage regulator that produces an output voltage lower than the input voltage. Assuming ideal components and a load made out of a resistor with resistance R, figure that is in left shows a buck converter with a voltage controller. The converter includes an output low-pass filter made up of an inductor with inductance L, and a capacitor with capacitance C to filter the output voltage. The higher input voltage relative to the output voltage causes the inductor current IL to increase when the transistor is turned on during buck converter operation. Since the inductor current cannot stop instantly when the transistor is turned off, the diode begins to conduct. The inductor current decreases because the diode is conducting when the voltage across it is zero. And typically, the buck converter's design goal is to reduce output voltage ripples. The current in the RL circuit exhibits exponential increase and decrease. Either the input voltage is equal to the voltage across the diode or it is zero. The magnitude of the ripple in the output voltage is determined by the converter's output filter, which smooths and attenuates the voltage waveform. In order to achieve the appropriate level of voltage stability, the filter design is crucial. Before the transistor turns on, if the inductor current drops to zero, it stays there until the transistor turns on. This is due to diode's restriction on the direction of current flow. The converter runs in discontinuous conduction mode in this situation. On the other hand, the converter works in continuous conduction mode if the inductor current never reaches zero during any part of the switching period and continues to flow. And also, by using a state space averaging during MOSFET on and MOSFET off, a linear time invariant model of the buck converter is generated in this section. The state space description of each of these systems is first developed, and a converter can be thought of as switching between various time invariant systems. The state space averaging method uses these state space descriptions as a place to start. By using this approach on the buck converter, a linear time invariant model with a state space description is produced. From this model, a number of transfer functions are eventually extracted, leading to the control to output transfer function that is maintained and shown in the right. The switching period Ts of the converter is determined by the control signal theta t in figure in left. It is significant to note that the changeover period in this figure is constant. However, the pulse width is changed in order to regulate the average output voltage. This is shown in the right picture, where the timing of the transistor turn-off is controlled by the pulse's falling edges. The duty cycle, abbreviated as dt, is a real number that falls between 0 and 1. It shows the proportion between switching period Ts and pulse width Ton. The average output voltage of the converter can be successfully controlled by adjusting the duty cycle. It is important to remember that the duty cycle is a discrete time signal, which means that it is defined only at particular time intervals as opposed to continually. Because of this, the duty cycle is represented by a series of discrete numbers that are related to the precise time intervals during which the pulses are present. As this project used and many other projects uses the PI controller to control the system. The PI controller, which stands for Proportional Integral Controller, is a specific type of controller commonly used in control systems. It is considered a special case of the PID, Proportional Integral Derivative Controller, with the key distinction being the absence of derivative term in the error calculation. of tuning a PI controller using MATLAB, the following general approach is typically followed. Initially, set the integral gain Ki to 0. This means that only the proportional term is active and the controller essentially operates as a P controller. Increase the proportional gain Kp gradually until the desired response of the system is achieved. The response can be evaluated based on criteria such as settling time, overshoot, or steady state error. Adjusting Kp allows for influencing the control signal proportionally to the error. Once the desired response has been obtained with the proportional gain, introduce the integral gain Ki into the controller. The integral term aims to eliminate any steady state error that might be present in the system and modify the value of Ki until the steady state error is minimized or ideally completely removed. This adjustment can be done iteratively, testing different values of Ki and observing the system's response. The process involves experimenting with different values of Kp and Ki, observing the system's behavior and fine-tuning the gains until the desired performance is achieved. It may require several iterations and adjustments to find the optimal values. Although MATLAB provides various tools and functions for controller tuning, such as the Control System Toolbox and PID Tuner, these tools offer automated methods and algorithms to assist in finding suitable values for Kp and Ki based on system analysis and performance criteria. It is important to note that the specific tuning process may vary depending on the system's dynamics requirements and control objectives. The general approach outlined above provides a starting point for PI controller tuning, but it's often necessary to tailor the process to the specific system under control. Although in this project, PID tuner is used to calculate Ki and Kp, since a fast tracking is required, Kp and Ki is equal to 0.471 and 4.9 or 0.49894 respectively. A step response of closed loop system with PI controller is also shown in the right figure. In order to find out how practical PI controller is, step response of closed loop buck converter without controller is also shown in the left. In the right, it is obvious that there is a steady state in response, and also it is shown that a step response is much slower compared to the control one. Alright, now as we have discussed, buck converters are an essential part of many electronic systems and applications. Effective and efficient controller strategies are also key to their success. And the field of DC-DC converter design and control is constantly evolving. New materials, technologies, and applications will continue to shape its future. I hope that you liked this video and it was helpful for you, and hope to hear your questions in the comment section.